Dear students, welcome back to another video lecture on the course Signals and Systems with course code 18EC45. As I have posted complete study material on module 5 earlier, from today onwards I'll be posting the video lectures on module 5. Module 5 deals with the study of Z transform, and in module 5 we'll be studying the definition of Z transform, properties of the region of convergence, properties of the Z transform, inverse Z transform, causality and stability with respect to Z transform, and lastly the transform analysis of linear time invariant systems. Before we directly jump into the study on Z transforms, we'll understand what is Laplace transform briefly and what it does, what Laplace transform does for continuous time signals and systems, and later we'll extend that study to define the Z transform and understand what Z transform does for discrete time signals and systems. Laplace transform is derived from Fourier transform itself, and Fourier transform success is because we are able to decompose most practical arbitrary signals into complex exponential signals, or complex exponential signals are generally called as sinusoidal signals. So any arbitrary signal, for example, we are taking continuous time signal represented by x of t here. Any arbitrary continuous time signal x of t can be written as superposition of complex exponential signals as summation ai e to the power si into t, where we define si as j omega into i. I is the variable on the summation. So for s equals to j omega, exponential e to the power j omega are the sinusoidal signals, and ai represents the amplitude of those sinusoidal signals for a particular frequency omega. That is the first reason why Fourier transforms are successful, or why Fourier transforms are famous. And the second reason is the exponential signal used to represent or to form the composite signal is a eigenfunction. Eigenfunction means when we apply eigenfunction as an input to a linear time invariant system, output from linear time invariant system will be of the same form as that of the input, but with a multiplying factor. So e to the power st, the exponential signal used in Fourier transform, is a eigenfunction. That is, if e to the power st is the input to linear time invariant system, then the output from linear time invariant system will be e to the power st itself. But that signal e to the power st will be multiplied by a factor h of s. H of s is a multiplying factor. Now these are the two reasons why Fourier methods are useful in analysis of linear time invariant systems. Now h of s for s is equal to j omega is called as frequency response of the linear time invariant system. Frequency response is nothing but frequency domain representation of the impulse response. Impulse response is the time domain representation. If you take Laplace transform of that impulse response, then it will be the frequency response represented by h of s, if s is equal to j omega. Now in Laplace transform, we generalize the concept of Fourier by not restricting s to be purely imaginary. That is, for Fourier transform, we considered s to be j omega, which is a purely imaginary quantity, which is used for Fourier. Now to extend Fourier into Laplace transform, will not restrict s to be purely imaginary. Will define or will generalize s as s equals to sigma plus j omega. So this time s will be having the real part as well as imaginary part. So the general quantity s, which is the variable for Laplace transform, is defined as sigma plus j omega, where sigma is the real part and omega is the imaginary part. And this generalization expands the domain of signals and systems, or the range of signals and systems that can be treated analytically with ease, that can be understood better. So if e to the power st is input to LTI system, then the output will be h of s e to the power st, where h of s is the eigenvalue and e to the power st is the eigenfunction. And h of s, which is the Laplace transform of the impulse response, is defined as integration minus infinity to plus infinity h of t e to the power minus st integration with respect to time t, where h of t is the impulse response. If s is defined as sigma plus j omega, then we'll be requiring two-dimensional space to represent the Laplace transform. On the y-axis, we'll be representing the imaginary part j omega, and on the x-axis, we'll be representing the real part sigma. So any frequency or any point on this s plane will be the coordinates of x, will be taken as the coordinates of x-axis and y-axis, which is the real part and imaginary part on the of the variable s. So Laplace transform for any arbitrary signal x of t, which is represented by, which will be denoted as x of s, capital X of s, is the Laplace transform of the time domain signal x of t, will be defined as integration minus infinity to plus infinity x of t e to the power minus st integration with respect to time. Now this is true if s is defined as sigma plus j omega. If in the value of s sigma is 0, then Laplace transform will be reduced to Fourier transform, because if sigma is equal to 0, then s will be equals to j omega only. So if s is equal to j omega, then the exponential in the integral will be e to the power minus j omega into t, which is the standard definition of Fourier transform. So for sigma equals to 0, Laplace transform will be reduced to Fourier transform. Now on the same lines, Z transforms are also the transforms to convert time domain signals into frequency domain signals, or time domain representation to frequency domain representation. And Z transforms are applicable only to discrete time signals and systems. Laplace transforms are applicable to continuous time signals and systems. And Laplace transform widens the range of signals and systems that can be analyzed, that can be understood. Likewise, Z transform are applicable only to discrete time signals and systems. As Laplace transform is the generalization of continuous time Fourier transform to be in particular, and the variable used in continuous time Fourier transform was j omega only, which will be generalized to sigma plus j omega in Laplace transform. Similarly, Z transform is the generalization of discrete time Fourier transform. So to define Z transform, we'll consider the definition of discrete time Fourier transform, which we studied in module 4. DTFT x of omega is defined as summation n minus infinity to plus infinity x of n e to the power minus j omega into n. Now the generalization here is e to the power j omega, which is the exponential signal used for discrete time Fourier transform, whose magnitude is 1. Now we'll generalize this to r e to the power j omega, which will be used for Z transform. Now the magnitude r of the signal r e to the power j omega will not be necessarily equal to 1. That is the generalization of Z transform here. E to the power j omega will be generalized to a quantity of the same angle. The exponential is e to the power j omega itself, but the magnitude is taken as r, which is some arbitrary value, which is not necessarily equal to 1. That means If r is equal to 1, we'll get discrete time Fourier transform. If r is not equal to 1, we'll get a new transform, and that new transform is nothing but the Z transform. For Laplace transform, we considered the variable s as sigma plus j omega. So in Laplace transform, we'll be working with rectangular coordinates. And in Z transform, we'll be working with polar coordinates, because Z will be defined as r e to the power j omega, where r is the distance and omega will be the angle. So in Z transform, Z is defined as r e to the power j omega. If we substitute, or if we use r e to the power j omega in the definition of discrete time Fourier transform, then Z transform will be defined as x of z equals to summation n minus infinity to plus infinity x of n z to the power minus n. Now this is the Z transform, or the frequency domain representation of the signal x of n, provided Z transform exists. So this is the definition of the Z transform for the arbitrary discrete time signal x of n, provided it exists. Now there is a condition on the Z transform to exist. We'll be looking into the convergence when the Z transform for a discrete time signals exist in the further video lectures. I hope you all understood the concepts for this lecture. We'll continue the same lecture in the next part. Thank you all.